material. So you should be able to know what is the heat capacity, and what causes the heat capacity, what is Dulong-Patet law, what is the thermal conductivity for metal and non-metal, what is the Wiedemann-Franz law to describe the relationship between thermal conductivity and electrical conductivity. Okay, the heat capacity is defined by the dE over dt, which means is the energy storage in a metal when you try to increase the temperature of material for 1 Kelvin or 1 degree Celsius. So this curve basically describes the whole chapter. We have classical theory and then we have quantum theory. In classical theory, the specific heat capacity is independent of temperature as shown here. So 25. Okay, remember that number. This is Dulong-Patet law. Basically, it gives you a number of 25 across the whole temperature range. While Einstein later discovered that the experimental heat capacity is different from the classical theory, which particularly at low temperature. That's because the heat transfer is through phonons. When you increase temperature at low temperature, the number of phonons increase. That's caused the heat capacity change. Heat capacity increase with temperature is a Paul law. And we also regard the electron component as the small percentage contribution of electron. That's because the electron is not a media to storage energy, to store the heat particularly. That's why the electron component is small in this curve. And the electron is not contribute too much to the heat capacity, but contribute a lot to the heat conductivity. So what is the heat conductivity? Is transfer the heat from one end from hot end to cold end. The driven force is temperature difference, and how fast it is conductive is due to the different thermal conductivity. And analog to the electric conductivity and thermal conductivity, which is described by the flow, heat flow is given by a temperature difference across the material times the thermal conductivity and times the geometry of the material. This is quite similar to the electric conductivity, which is a function of conductivity and the potential difference. So why you want to seek a good thermal conductor, then you always look for a good electric conductor. There is a relationship between thermal conductivity and the electric conductivity. The relationship is described by this law. And thermal conductivity over the electric conductivity is a constant, which means the higher thermal conductivity metal tends to have higher electric conductivity. So here is a curve of a list of metal which has different electric conductivity and thermal conductivity. As you can see, if you want to look for a good thermal conductor, then you measure the electric conductivity, which a higher electric conductivity, the metal, that is what you will find. And how heat transfer in a non-metal, say insulator. There is no electron, no free electron inside the insulator, ideally. So how heat transfer, how heat is conductive? The only medium is lattice vibration, which is called phonon. So if you heat the material from one end to the other end, the hot end side, the lattice vibration becomes severe, and the number of phonons increase. And the number of phonons as a quasi-particle diffuse across the entire material to the cold end, that's transfer the heat. That's the thermal conductivity in a non-metal.